Perfect. Okay. There's something called the intermediate value theorem. Let me explain what that means. Okay. So you guys or actually David, you asked I think yesterday about like what does this like little e thing mean?
Yeah.
So this means that A and B are real numbers. Because you're saying they're the element of the real numbers. And the R with like that looks kind of weird like that means real numbers. And the E stands for elements. So those are just real numbers. And A happens to be less than B. Okay, keep that in mind. A is less than B. So F is continuous on A to B. So let me draw a picture for you guys. That'll be good. Let's draw a picture. Here's A. Here's B. 2-degree A is less than B, right? Also, you're gonna have a curve that does, something kind of weird. Let me change colors. Let's say my curve does something kind of funky like this. I don't know. I'm just totally just kind of just making this up. Okay, let's say my curve does that. Will this be continuous? Yeah, this is totally, I don't see any breaks in it. It seems nice and smooth. F of A is a Y value A. F of B is a Y value B. Are those Y values the same? Nope, they're not the same. They're totally different. In fact, actually, F of B is positive, right? And F of A is negative. Okay. You don't have to make it that way, but I just felt like it. Okay. Then in the interval from A to B, this is the intermediate value theorem. Intermediate means in between, right? When you think of the word intermediate, you think like in the middle. Like if you're an intermediate level for like a certain skill, you're kind of in between, right? Then F takes on every value between F of A and F of B. So what do you think that means, takes on every value? Let me give you a hypothetical. Yes, Sean, go ahead.
It'll touch, and like for in between those two, like F of A and F of B, will touch every Y value on the variable.
Yeah, let me give you an example. Yes, that's correct. For example, let's say A equals 1 and B equals 4. And let's say F of A is like, I don't know, -5. And let's say F of B is 6. What this means is that any point with X between 1 and 4, Y will equal some value between -5 and 6. Actually, let me change this some value. That's a little vague. Will equal all value. Here we go.
Oh, geez, that's terrible. I'm sorry you guys didn't do that. Sorry, it'll be better. You did test it out this morning. It's going to be a great projector. It's going to be awesome. Anyway. So, yeah. So, like, for example, what FA is -5? What FB is 6? So, do you see how in between 1 and 4, in between my A and B values, any Y value could be had between -5 and 6? For example, can my function equal 0 in the interval from 1 to 4? Yeah.
Yeah.
Because it's 0 between -5 and 6. Yeah. Can my Y value equal 5.98? Sure. Because isn't 5.98 between -5 and 6? Now, can my Y value equal 6.2? Maybe. I don't know. Maybe. I'm not sure.
Because my graph could have done this, by the way. If I so desire, and you will investigate this theorem again when you get to calculus. And you actually kind of see it in another light as well. But your graph could have done this, by the way. Totally could have done that.
That doesn't have to be the highest Y value in the interval. That could be, it could be way up there. That doesn't have to be the lowest Y. It could be way down here. But is every Y value between -5 and 6 still taken on? It is. As long as you're continuous. You have to be continuous.
If you're not continuous, all bets are off. You have to be continuous for this to happen. So that's the theorem. Does that make sense how the theorem works? But if any vagueness, please let me know if anyone's. It's sometimes a hard one to explain because I even sometimes confuse myself with it. So even though I've been teaching this theorem for a while. So does that make sense? All y values can be had as long as you're continuous from a set interval, closed interval, mind you, from A to B, or in this case, 1 to 4. I hypothetically made that up. And I hypothetically made some y values. So all y values between -5 and 6 will be taken on. Cool? David, yes, you have a question.
I don't get what F. I don't know.
Ask away, please.
I don't really get what it means F takes on every value.
So for example, f of A, I chose to be -5. F of 6, I chose to be 6. Sorry, f of 4, I chose to be 6. So all y values between -5 and 6 will be part of my range. So if I look at my domain from 1 to 4,
Okay. Oh,
my range is from -5, 6. And so at least one time, what y should equal some number between -5 and 6 in that interval.
Okay.
Actually, that was a great way. I should have wrote it down like that. Sometimes I think of a great way of explaining and I forget after 5 seconds. So, well, I was recorded. So here we go. I recorded. Okay. So let's look at example 4 now. Okay. So in this case, use the intermediate value theorem to show that there has to at least be one real zero in the interval from 0 to 1. So here's the deal. I'm not gonna be able to find it precisely because this is not factorable. This is a weird polynomial, right? But if I set this equation equal to that, to 0, right? Can this work? So the question is this possible? And the answer is yes. Because of IVT. I don't feel like writing it out. IVT is short for intermediate value theorem, just so you know. So just get used to it. IVT, intermediate value theorem. And y, g of x, that's a terrible looking g, is continuous on my interval from 0 to 1. So let's do it. What's g of 0, guys? And what's g of 1? Great. So then here's how you make a statement. So what I'm looking for is this. I want you to tell me IVT applies. I want you to tell me it's continuous. I want you to compute this. And then I want a concluding statement. So you got to tell me IVT, continuous, give me the values at 0 and 1, and then we make a concluding statement. How do you write the concluding statement? And this is, I'm not going to be so picky about it, but just make sure you're hitting some of the key points. It's a polynomial function. Polynomial functions are always continuous, right?
As long as there's no root order.
It's polynomial. It's all good. Yep. Okay, that's one way you could say it.
G of x will equal 0 at least once in an interval from 0 to 1 due to IVT says G of x is a continuous line interval, and that happens. So when I think about it, I kind of just repeated myself. Because really, I just took these three things and just kind of articulated it in a more grammatically better way, I suppose. But what I'm looking for is that statement. I'm looking for that statement. So I guess you don't have to say IVT like this. You can just, it's kind of taken care of here. To be honest, I think this statement actually takes care of all this. If you said that, you're good. I think this actually is sufficient, and you don't need all this junk here. I think this junk is just helping make sense of it. That, oh yeah, there's IVT going on here. Oh yeah, it's continuous. Oh yeah, it equals this. Okay, yeah. Really, I need this. That's what I need.
And the things I'm looking for is you gotta tell me IVT. You gotta tell me continuous. You gotta work these out.
It's not continuous, I don't want to play.
It would not work. It would not apply.
So how do you?
It's a polynomial. That's how. All polynomials are continuous.
Oh, you have a good.
I'll give for you a not continuous one. Yeah. I'm just kidding. Actually, that's a great test question. I will ask the reverse of it. No, just kidding. I'll leave it like this. You could ask like, why would IVT not apply? Actually, I've done it for an AP Calculus AB. I have asked, why would IVT not apply? And that's because it's not continuous. So you have to have continuity. Like if I gave you great question, actually,
Thomas, you really voted that's a really good test question. Yeah. So what if you have this y equals 1 over x minus 1? And what if at the interval from 0 to 2? So is it a guarantee? Like for example, what's this f of x, right? What's f of 0 here? Yeah, 1. What's f of 2? 1. Okay, is it a guarantee that y will equal 0 in the interval from 0 to 2? It's not, because what's happened between 0 and 2? Do I have discontinuity happening between 0 and 2? And x equals 1. I do have a discontinuity happening. So IVT would not apply here because guarantee them have discontinuity. So I don't know if all values can be had between -1 and 1. I don't know. And actually, I know it won't be because I know how that graph looks. Well, 0 is a horizontal. I know that. But yeah. But in that case, I can't use it because it's not. Because the graph looks like this. Oh, the graph looks like this. So just by looking at the graph, I know why I can't. But the IVT confirms that. So that's actually a great question. I'm not being facetious. I actually do like that question.
I kind of asked the opposite of it. Anyway, let's keep moving. I think I kind of beat that one to death. But that's IVT. There you go. We did example 5, right? And we did example 6. And we did did we do 7 and 8? No, we did not. Okay. And we do 9 either, right? Okay. So I'm going to go back to this box thing because I actually can do it better now. I was pretty bad with it when I first showed it to you guys. So remember I showed you this, right? If you have x cubed, I'm going to do 3 columns. I'm going to put x in -4 and 5x cubed. So this is really no different than like, you guys have seen these kind of problems in the past. I know that. I know you guys done this, right? And have you guys ever combined it using a box like this? If you came from our middle school, probably did do this. You guys remember doing this? You have x squared and -x and -4x and +4. Combine everything, right? It's the same thing. You're just reverse engineering it, right? Because now you're trying to figure out what to put on the outsides. So I know x minus 4 is off to the left. I know 5x cubed has to be one of my terms. And if 5x cubed is one of my terms, then this has to be 5x squared, right? Because isn't x times 5x squared 5x cubed? Okay. Now, how do I fill out the rest of this box? when you have numbers on the outside, when you multiply them, they converge to where they meet, right? Like if I multiply negative 4 or 5x squared, what do I get in this box here? Good, let's do it. Negative 20x squared. However, and this is the part that's not terribly obvious. This is the part where people get a little confused. I need you guys to be really present to this. Negative 20x squared. What do you add to negative 20x squared so that you guarantee negative 6x squared? 14x squared. Because you need, like, for example, when I just did that problem down below over here. Remember, like x minus 1, x minus 4. Excuse me. Thanks. Remember x squared, negative x, negative 4x, and 4, right? And you have to add these up to make sure you get negative 5x. When you foil the process, right? So it's the same thing here. I have to guarantee that these add up to what? Negative 6x squared, which they do. So if that's the case, what am I going to put right above 14x squared? 14x. Good. So therefore, this is negative 56. Negative 56x. Does that make sense? I got that? Okay. Now
Now that negative 56x, so negative 4 times 14x is that. Look at what we're dividing into. Is there an x in my numerator here? No. So if that's negative 56x, what do I have to put over here so it cancels with this? Yeah, because I need these to add up to 0x. See, these add to negative 6x squared. Cool. This has to add up, because remember, the whole point of this is you want this times x minus, you want something times x minus 4 to equal that. So
what is our intention, right? Our intention is this. Sometimes we get away from it. What do we want? We want x minus 4 times a question mark to equal 5x cubed minus 6x squared plus 8. That's what we want. So I have to figure that out. So if I have negative 56x, negative 56x, sorry, you have to have 56x. Now, what do I put up here? 56. That becomes negative 224. Don't worry, I'll let you have a calculator. Then I need to do one more column. Because I need 8, right? I need 8. Let's say 224. What am I going to add to this number? You got to be 8. Will it go, Sean? 232. Awesome. So I need that to be 232. And that's how I'm getting 8. So what happens is that becomes a remainder, right? So it's kind of weird, but this actually becomes 232 over x minus 4. Because if I multiply this by this, I do get 232. So final answer is 5x squared plus 14x plus 56 plus 232 over x minus 4. So if I were to multiply that by x minus 4, by the way, if I multiply these together, what would I get? 5x cubed minus 6x squared plus 8. Guaranteed I would get that if I were to multiply x minus 4 to that junk. Really, what this really is, this is a glorified factoring method. We factor out x minus 4. We forced the issue. That's all this ever is. It's a glorifying factoring method. Why do we care about this? Because when you do move on to calculus, whether I teach you calculus or someone else does, there's going to be a moment where you're going to be using some sort of calculus principle, some kind of technique. And in order to be able to do the problem, you're going to have to do this. You have to somehow simplify this equation down to this way so you can actually do whatever calculus process you're being asked to do. So this is going to be an algebraic technique. You need to be able to pull it in your back pocket very quickly. So it will come back. And it comes back with a vengeance. So you have to be ready for it. Because when you least expect it, like, oh, I can't do this. And so, oh, just do synthetic or do long division or do this division. Like, oh, okay, you're right. Let's try it again. By the way, if you want to see synthetic, I'll show you really quickly. I'll leave up to you what you want to do. Synthetic division looks like this. You guys see how I set this up? How did I set this up? Why did I put 4 on the outside? Because x minus a, right? Because what's happening is that what am I really factoring out? X minus 4. If I factor x minus 4, what's my 0? 4. So I put 4 on the outside. And why 0 between -6 and 8? Placeholder, thank you, yes. Now, the process, in case you guys forgot, is you bring down the 5, multiply, and add. And you rinse and repeat. It is easier, I think, doing this way. Where I think the box method helps is when you can't do synthetic division.
Was that? When it's not linear. If it was like x squared, or if it's like a coefficient that's not 1, you could do synthetic division, but you have to factor. I'll show you one right above. Yeah.
Yeah, so like for example, yeah, for example 6. If you want to do that, for example 6, you'd have to actually pull out that 2 and make it x plus half. And then you have to divide all these by 2. And now you got a bunch of fractions, which is really nasty. I think the box method would work great for example 6. And likewise for example 5. Or you do long division if you want. It's up to you. Let me go back again to this right here. So then when you do this, what do those numbers represent at the bottom? They represent the coefficients of your answer. And you always go 1 degree less because you have x cubed over x. So it becomes 5x squared plus 14x plus 56 plus 232 over x minus 4. That's how you kind of wrap it all together. So for example 8, I'll leave it up to you if you want to do synthetic or the box method. It's up to you. I don't care. You guys have a particular way I want to do this? Here, I'll do the box method. I'll do it quickly. Here we go. Okay, it's degree 4. The 4 columns. I might need a 5th column for the remainder. X and 3. X 4. Okay, I'm gonna go faster, guys. Let's go. What I put up here? X what? 3x cubed. Do I have an x cubed in the problem? Nope. Negative 3x cubed. So what goes up top? Negative 3 x squared. What goes down here? Negative 9x squared. What do you add to negative 9x squared to get negative 10x squared? Negative x squared. That's negative x. Negative 3x. What do I put in the top right corner, guys? Well, negative 2x. 2x. Okay. So then, oh, sorry, negative x. Sorry, sorry, just x. My apologies, just x. So it's 1. And then that becomes 3. But I really want 4. To do side box for remainder. That'd be 1. Then you get that.
-2 plus. -2 plus 3.
So that's the way you can go about it. Okay. We're okay with that? So x cubed minus 3x squared minus x plus 1. So plus 1, by the way, is positive. Plus that remainder. And remember, all the diagonals have to add up to all the terms into what you're dividing into. All right, let's keep moving. Okay, example 9. Suppose you wanted to do that and you really want synthetic division. Is there a way to do it? You can using synthetic division, but I'll do this instead. Yep, let's use the box method. 2x and 1, 8x squared. Okay, what do you multiply 2x into 8x squared? 4x. Okay, do I see an x in this numerator? So you got to put negative 4x, cancel it out. Therefore, this has to be negative 2, and that becomes negative 2. But what do you really want? You want a negative 5, right? If I want a negative 5, what will I put there? A negative 3. So it becomes 4x minus 2 minus 3. Now, here's the thing that's kind of cool. This is the thing actually. This actually is a really cool problem, and I'll explain why in a moment. Hold on a sec. Let's see. Desmos. Okay, what was our equation of y equals 8x squared? Someone tell me minus 5 over 2x plus 1. Okay, that's a pretty funky graph, right? Let's graph this. Y equals 4x minus 2 minus 3 over 2x. It's the same thing. They're the same graph. They should be, because that's what we did. All we did is we did a cosmetic change. Now, why does this matter?
Why do I care? Let me write this. It comes back to end behavior. We're going to talk about rational functions later in this unit. Look at the ends of the graph. Look at that far right and that far left. Doesn't that look pretty linear? In fact, actually, 4x minus 2 is pretty darn close to that portion of the graph. Likewise down here. Because think about what happens when x gets bigger?
That goes to there.
Well, yes, good, Sean. When x gets really big, that fraction pretty much is negligible. It's like 0.00 whatever. So what are you really stuck with when x is really big? 4x minus 2. The graph behaves, the ends of the graph behave like that linear expression. When x gets really positive, like going towards positive or going towards negative, that's why we have to rewrite this, because it's not painfully obvious for that original. We have to do this cosmetic change to see, oh, yeah, the ends of the graph will behave like 4x minus 2. That's why we have that
Can you
technique.
graph 4x minus 2 and see that?
Sure. Yeah, 100%. Here we go. See, in the middle, no. But as I do this, they overlap. Or close to it. No, they don't exactly overlap, but they get pretty close. See, they diverge. And guess what? They converge. Yeah. That's the reason why we have it. It all comes back to end behavior again. All right, good. I feel better about this. That you guys seen this. All right, let's do a little. What time do we end class today? 1. Oh, we're good. Yeah, let's keep going. Okay. All right. Yes. Oh, go Laura. Yes. Go ahead. Sure. Yeah. What you want to do is this. You factor out the 2 from the bottom. So it becomes this, right? And up top, you have this 8x squared minus 5. Now, what you do is that 2 that's on the denominator, it actually will now move its way up top like this. And now it becomes this. Because what happens when you divide by 2? What's the equivalent of dividing by 2 multiplied by half? See, if I factor the 2 from here, and even though 2 is not a factor of 1, I force it out by dividing by 2. And then if I'm dividing by 2, it's equivalent to multiplying by half. And I distribute the half to get 4x squared minus 5 halves over that. So it's a little bit of fraction stuff you have to do. If you don't like fractions, this is not going to be a good technique. And then what you do is you do negative half, 4, 0, and negative 5 halves. You bring the 4 down, multiply becomes -2, add it becomes -2, multiply becomes 1, and that becomes a -3/2. So what do you really got then? 4x minus 2 minus 3/2 or x plus half. When that 3/2 is divided by x plus half, it could be rewritten like this. And you get back to that. It works. I personally like the block stuff better because it's cleaner without the fractions. This can get really messy. Well, whoever made these notes didn't know about this box method about 5-6 years ago. We just learned about it last year. So I think it's really neat. It is groundbreaking. 100% it is. Yeah. But that's how you do it. Okay. Let's move on, guys. All right. Remainder theorem and factor theorem. I don't know if you guys talked about this last year. Okay, guys, quiet, please. So the one thing you got to keep in mind, let's come back to, can someone tell me the answer for example 8 again? What was the answer for example 8? Can someone tell me that again? What was the last part? Sorry. Perfect. Thank you. Okay. Okay. What was my remainder here? For example 8. The remainder is 1, right? When I did the division, because that's my remainder, right? Well, here's the thing. What if I plug in? What if I call this f of x? Okay. And what if I plug in -3? Let's work it out. You don't have to write saying, just watch for now. If I were to work this out, geez, sorry. You get 81 minus 90 plus 6 plus 4. What does it all want to becoming? If you combine all that. 1. That's the same thing as remainder. That's not a coincidence. That is not a coincidence. Personally, plugging 93 into that without a calculator could be a little painful because you could make materials there pretty easily. If you mess up the negatives or the root, the exponents, whatever, right? So the point is that if you're dividing by x plus 3, whatever the remainder is the same thing as plugging in f of -3. Whatever makes that 0. So if you're told like, oh, I want to value this at f of -3, you can just do synthetic division or the box division, and the remainder will be your answer. You could do that. That's a possibility. That's what remainder theorem is all about. That's what it's telling you. I won't do the formal proof because that'll take a while. And actually, to be honest, I don't remember the proof, so I won't do the formal proof. Guys, quiet, please. But what if your remainder is 0? Then it's a factor. Then it's clean. It comes out clean if it's because f of a equals 0 then. Guys, I need you to focus, please. Guys, enough. If f of a equals 0, then it's gonna be a factor. Because you have a 0 remainder, right? If you have a 0 remainder, then it's dividing out cleanly. Then whatever a is, x minus that number is a factor of the function, or a comma 0 is an x-intercept. Let's do some practice so you guys can see how this works, and then we could do the homework quiz. More I think about it, I don't know if I'm going to do 11 and I'm just do page 10. I think that's good enough. Then I think we're okay. Yeah, I'm not gonna do the rational 0 test. I'll save that for. I don't think the homework requires you to use that. Let me see here. Let's make sure. Yeah, I don't think we need to work. I think yeah, we'll be good because that doesn't happen until homework 5. Yeah. So let's just do page 10. We're good. Okay. So here we go. Use synthetic division to evaluate that. So here's what you do. You could do 2 ways. You do f of -3 by direct substitution, which, yeah, you could do, but it could take a while. Or you could divide f of x and the remainder equals f negative 3. That right there, guys, is a remainder theorem. That second way. So let's do it. I'm going to do it the second way. I'll do synthetic, just because I think in this case synthetic's probably a little faster. So put negative 3 on the outside, and you get kickstart by bringing the 3 down, multiply, add, and rinse and repeat. Boom, done. 6.
If I were pulling negative 3 straight up, let's see here, I got 3, negative 3 cubed. You can see it's gonna take much longer to do it this way, and I might make a mistake. That's 81
Oh,
plus 36.
so when x equals 3, x is 6.
Yeah, I already made a mistake. See, that's just a negative 81. There you go. I already made a mistake. I didn't mean to. That's what negative 45 plus 51. Yeah, you get 6.
So x equals negative 3.
Correct. Correct. So that's a very nice, nifty technique for evaluating using the remainder theorem. And when you divide, you have options as well there. Now you branch even more options. You can do long division, synthetic, or the box. I think synthetic was probably the better technique. Will not do long for sure. Maybe you could do the box method. That's fine. But I think the synthetic is kind of more seamless in this regard. But synthetic's not always going to work for some situations, like with dividing by a linear expression with a coefficient that's not 1, or divided by a non-linear expression like x squared, x cubed, so I don't know. Let's look at example 11. This will be our last one. We'll stop here and we'll do the homework quiz after this. Show that x equals half is a 0 for that function, and then find the other zeros. Great. Here's what we're gonna do, guys. Let's do synthetic again. All right, let's get kickstart. How do I get kickstart? What do I do? Do the 2 down. What's the first next step, guys? Half of 1. Sorry, half of 2 is 1. Sorry, I'm talking too fast. And then add it, and then rinse and repeat. Look at that. You should get 0 because they said so. We should get 0. Now, what do you want to do with this? What does that represent? Okay, let's factor out 2. Is that factorable? Sure. If it's not, use quad form. It's fine. We're completing a square. But it's factorable. What are the factors? Perfect. There you go. That was not painfully obvious to see if 5 and 2 are factors of this, of the original stuff.
When I look at that, that was a little daunting. It's like, well, I don't know if 5 and 2 are factors of it. Well, they are. Because now I know, now I've expanded my horizon. I figure, oh, okay, I could factor this out. Again, division is just a glorified way of factoring. That's all there is. Essentially, you're dividing x minus 1. Big 5. But yeah, that's just a very nice technique.
Did Mr. Band do this with you guys last year? Do you guys remember? I'm meeting with him tomorrow to see what he's done with you guys. So yeah. Yeah. So we're gonna be taking our time with it. Okay. Cool. All right. So homework will be homework 4. Okay. Which will be pages just page 15. 1 through 5. I'll make sure this is in school, Gene. But for now, let's do the homework quiz. You have the rest of the class do the homework quiz. Let me go pick them up from the copy machine. I'll be right back.
Let's see what we got. Once we get the money, once we get the-
Alex got the thing with all the.
What's all the?
Okay.
Wait, what?
Crazy. Wait, wow.
It's like squid food, but it's shrimp game. But it's so fun. It's so.
Not me. I don't engage in this.
Crazy.
It's so.
That might be a new low, bro.
So
That might be a new low. That might be a new low. You went
so
from
fun.
you went
Alex
from
got
blue to
that.
profile.
That's a really, wait, let me see the final answer.
Yeah,
Maybe the wrong answer
I
easier.
can't find it.
Blue GeoGuessr profile.
GeoGuessr.
We're all like shrimp game. Shrimp game. It's so fun. Hop on.
Mr. E was like,
It's just like
Squid Game, bro. Mr. E would like that. He likes Squid Game.
I played it somewhat. Oh, sorry, that means, yeah.
You guys on voice chat? Wait, were you guys on voice chat? Those are so fun.
Everyone except for one person actually.
Wait, is it Joe?
No, yeah, you can voice chat.
Oh, so they collect a bunch of people.
Like in the group, like in the. It's on this one.
Duke it out for.
This guy was like. And then he was the only one that.
And if you lose, you literally die.
Yeah.
All but one of them died.
Yeah.
Everybody died.
Oh, deeper think questions. I like this one.
They're possible, there's more than this infinite possibilities. Just make sure it makes sense, and in your graph has to make sense with your equation you come up with. So you come up with an equation, there's not just one answer, there's more than one possible answer.